Okay, this is set number 5 on angular momentum. First is a multiple choice question, where we have a disk of mass 2m and a child of mass m. Our goal is to increase the omega of the system. So we want our ride to end up going faster. Our options are have the kid move to the center, because that would increase the angular momentum of the system. Have the kid move to the center because that would decrease the I value of the system. Have the kid move to the edge because that decreases the angular momentum of the system. Have the kid move away because that decreases the moment of inertia of the system. So first, what is our system? Our system is the boy and the merry-go-round. If there are no external torques, let's think about that. The only torque external there's the pivot here, that's a force, but it's got no lever arm. So there is no external torque. So therefore L initial equals L final. So that means anything that's talking about changing the L value of the system just can't be the correct answer, because here angular momentum is going to be a conserved quantity. In fact, L initial equals L final is what's going to get us to our answer, because we can say I initial, omega initial equals I final, omega final. So you can see if what we drop the I value, then our omega final value will have to go up. So we want the option to decrease I. So the question is, which one of these actually decreases I? So remember when we were dealing with the bricks and we pulled them in, and that made us go faster? So we were taking the point mass and we're putting it in the center, decreasing the R squared value with the point mass. So this is the option. Our answer is B. That's the only thing that can be done, and the proper reasoning for why the boy should move to the center of the ride. So if he'll move to the center, he'll decrease the I. If the I decreases, momentum is conserved. There's no external force, so omega will increase. Okay, let's see. Next part. So the next part of the question is asking us to actually solve what is the omega final that occurs. It tells us the child is mass m, the disk is mass 2m. We know the moment of inertia for a disk. And we know he starts out at R over 2, he ends up in the center. So we're going to have our boy go from L initial equals L final. We're going to take the problem from R over 2, this is a subscript to myself, moving to R equals 0. So what we can fill in is I initial, omega initial. Omega initial is just given in the problem, it says it's initially rotating that much. At the end, let's fill in I final and omega final, where we're trying to solve for omega final. So let's just go ahead and we'll expand each one of our things. So the initial I value is going to be because the boy is standing at R over 2. So we're going to have a disk, which is 1/2. The mass of the disk, mass of the disk, 2m, times times the distance of the disk, so the whole radius, plus the point mass of the child times the distance of the child. Then for I final, we'll have omega final, we'll just leave that in front. For I final, we're going to have 1/2 the mass of the disk, the radius of the disk squared, plus our point mass, m, at a distance 0. So let's simplify and solve for omega final. So here we're going to have m r squared plus m r squared over 4 omega naught equals omega final times m r squared. So then we can just do this addition. This is 5/4 m r squared omega naught. Let's divide by m r squared. Then I'll leave us with omega final. Just divide that side and simplify it a little bit. So then these cancel, and omega final is faster. It's 5/4 omega initial. With that, we can actually find the impulse that was delivered to the disk. Because the system's I value doesn't change, but the disk's I value does. The disk is experiencing a torque from the boy, and so we can either do torque times time, that's an angular impulse, or we can look at how the angular momentum changed. So let's look at the angular momentum changing. So what we're going to do is find out the impulse, the angular impulse on the disk. So that means we're only interested in the change of the angular momentum of the disk. So L final minus L initial of the disk, not the system. There's no delta L of the system. So if we go to fill this in, we can say our final L is going to be I omega, where we have 1/2 2m r squared. That's our I value. Our omega final value is 5/4 omega naught. So what I'm doing here is I'm just filling in I final omega final minus I initial omega initial. So I plugged in I final omega final minus I initial. Let's make that easier. Omega initial. So we can see the angular impulse, if we want to just simplify that a little bit, is mr squared times 5/4 omegas. I'm pulling that out to the front. So omega naught is in everything, mr squared is in everything. We have 5/4 minus 1. So the angular impulse is actually a negative number, right? No. Positive number. mr squared omega naught 5/4 minus 1 is 1/4. So our angular impulse is mr squared 1/4 of the initial omega value. Remember what an angular impulse does? That's what changes our angular momentum of the disk. The boy's angular momentum will also change, so the system remains the same, which is what we did up here. Well, here we looked at just the disk.